Hello everyone, I'm Wissam Saabe and I'm application engineer at AMCAD Engineering. I'm glad to participate to this online event and present our very recent work about behavior modeling of transistor and power amplifier. So the first part of this presentation will concern behavior modeling of transistors for circuit design. We will present in details the EPHD model and its applications in two power amplifier designs. In the second part, we'll show a behavior modeling solution for RF circuit to address system design. We'll show the interest of using these modeling techniques for the advanced antenna system and linearization system. So let's start with transistor modeling. As you know, there are different types of modeling that we can use for amplifier design. The first one is physical model. There is also the compact model, and then the PhD model. For the physical model, it's the blue region that you can see here. We know that we can get a very good extrapolation accuracy, a very good insight of the physical structure of the model, and the operating range can be very high. The only problem with the physical model is that we cannot design a PA. Designers cannot simulate a physical model due to convergence issue related to the very high number of parameters. So the physical model is specifically used to design transistor components. The second option is the compact model, which has been used for a long time and has very good results. This model will be very good on convergence. The operating range is very fair. Extrapolation accuracy is also very good, and we get some kind of insight of the physical. Currently, foundries can provide compact models of their transistor to use for different applications, but it takes several months of development. The issue is that if you want to make a design for one application, it is not profitable in this case to develop a new compact model. To that, people are using PhD model. The PhD model gives you a good and easy modeling process because it's based on measurement. From this measurement, you are able to extract a model which will work for your specific application. The drawback here is that it's very limited in terms of convergence, operating range, and physical insight. So AMCAD has been working lately on an advanced model called Enhanced PhD model, or EPHD model. So what's the problem that we want to solve with this model? So first, we would like to increase the convergence, mainly for the load impedances. We would like also to increase the extrapolation accuracy. And the easy modeling process is something that's already available with the PhD, and the EPHD can use it also for the circuit design. So that's what the EPHD will be able to provide you here, and that we are going to present you. As mentioned previously, to create one model for one application using a package device, the compact model is not the most efficient way. Indeed, you need to spend 6 months for extracting a model for your own wafer device, and then for the package, and then implement everything in one model and check if it's in agreement with S parameter measurement and also in a high power level in load pool condition. All that in order to be able to design your PA. And these conditions will not be, you will not be the first in market. So we would like to present you with this modeling solution a process to reduce the time to market by extracting an EPHD model and use it for the PA design. So for that, you will use a black box model based on a set of equations. So I believe some of you are familiar with the traditional PhD model. The PhD model is a linear effect of the power wave F2 on the nonlinear response of the model. So if you are tuning at a certain impedance, you are able to extract a PhD model at this impedance, and you are able to see the linear influence over the nonlinear model, and that's the first line that we have here. AMCAD added another set of equations to extend the power expansion order. So what does that mean? it means that instead of having one model for one impedance and see a linear variation or linear influence over a very small area around the impedance, we're going to create a model for a pattern of impedances which will have a nonlinear influence over the whole pattern. So our equations are nonlinear and are able to predict the response of the circuit over a large area on the Smith chart. The setup to do the measurement is based on the load pool setup using an harmonic load pool tuner and with the information about the amplitude and the phase at the harmonics of the AB power wave. So we measure the AB power waves at F0, 2F0 and 3F0 if necessary, with amplitude and phase using a phase reference and a VNA. Then with that we are able to extract the EPHD model. In this circuit design example, we would like to create a model in order to design an hybrid Doherty power amplifier using available on-the-shelf package design. This work has been done for the French Space Agency CNES, and the power amplifier made is currently used by CNES at C-band. So this is a Doherty amplifier configuration. The first thing is you will not be able to predict the load modulation because we have two power amplifiers. There is the carrier and the peak. The peak is mainly working in class C, so when the power is low, this power amplifier is actually not passing, but there will be a modulation of the impedance that will be seen here, and that will create some issues. If this modulation is optimized, the efficiency of the overall amplifier can be increased over a large dynamic power range. First, we extract a model of a class AB transistor at 3.7 GHz. The black dots on the Smith chart are the pattern used to extract the EPHD model. So we can see that the AM characteristic of the model and the measurement are in a very good agreement. Same thing on AM/PM characteristics, on efficiency, on drain current, and also on output power at 2F0 over the input power range. So we can see that our model provides a very good agreement with our measurement for class AB. Class AB is not the most challenging operating class compared to the class C. As you know, in class C we have a sharp gain expansion, and in this case we are able to extract a model that is in a very good agreement with the measurement, as you can see here. Then what we did is we took these two models, the AB class and the C class, and we put it in a commercial circuit simulator, and we designed a Doherty power amplifier based on these two models, and we created this power amplifier. The first thing we try to check is the simulation convergence, the interpolation and extrapolation capabilities, and see if we have a little bit of freedom when we are designing our PA. So we have done a model at 3.7 and 3.95 GHz, and we simulated this model for the Doherty power amplifier for frequencies inside this measurement band. So we check the frequency interpolation of this model. We can see the load modulation over frequency for the AB and C classes, and this is the most challenging part because the class C at low power has a load modulation outside the Smith chart. So in this frequency interpolation configuration, we didn't find any convergence issue of this model. Another aspect in the technology or in the design of the Doherty power amplifier is the design of the combiner. What we do here is we change the length of the combiner, and this automatically affects the impedance of the two power amplifiers. So the first, for the class AB, for the class AB, this is the load modulation that we have on the Smith chart when we are changing the lambda quarter length of the combiner. In class C, corresponding to the peak, we see a very large variation of the load impedance, when we are changing the length of the combiner. And yet, by doing this and simulate our Doherty power amplifier, we still see that the simulation results are following the characteristic of the Doherty power amplifier. So the power of this model is that even if my impedance is very far from the region where I extracted the model, we are still able to predict the behavior of this power amplifier. So we did the design of and we realized this power amplifier at C-band, and we measure it at 3.8 gigahertz. And here we can see the results between the measurement and the model of this Doherty power amplifier at 3.8 gigahertz to prove the frequency interpolation and the impedance extrapolation. And we can see that our efficiency is in very good agreement between the measurement and the model. Same thing on the gain and the output current of the two power amplifier, the main and the peak. The second example about the use of EPHD model is in the design of a 60 watt power bar amplifier in the GaN technology. The work consists of modeling one transistor in class B at one frequency and use this EPHD model to design the PA. The transistor was characterized at fundamental and at second and third harmonics. The load impedance patterns are described in this Smith chart. After the extraction, we compare the model to the measurement based on the impedance described with the red stars on the first Smith chart to see the interpolation and extrapolation capabilities. And we get very good results on efficiency, drain current, AM/PM characteristics, and output power at F0 and 2F0. We compare here the EPHD model and the compact model on measurement performed on the transistor. This transistor is loaded with the optimum impedance corresponding to maximum efficiency. And in this condition, we observe that the EPHD model provides the same level of accuracy than the compact model. The EPHD model and the compact model were used in the PA design. The PA was made using compact model-based design. And here we compare the performances of the two simulated designs on the measurement at 5 dB compression gain over than 1 GHz bandwidth. So it should be noted that EPHD model was extracted at only one fundamental frequency, and despite this, the simulation presents very interesting results on output power, efficiency, and drain current. To conclude in this part, we did the design for two models in A, B, and C classes, and we showed actually a very good agreement between the model and the measurement. This technique is able to reduce your measurement time greatly compared to traditional method, and we are able with a simple load pool measurement to extract a very strong model. So we use this model in a realistic configuration of a Doherty power amplifier, and we were able to predict not only the interpolation in terms of frequency, but also the extrapolation in terms of impedance modulation. So we believe that the EPHD is a very promising candidate for the design and realization of power amplifiers because it's robust, reliable, and easy to do. We have seen how the EPHD model extracted from load pool measurement allows to design power amplifiers. We are going to see now how PA measurement or PA simulation allows to extract behavior models to design system through two application examples, which are advanced antenna systems and linearization systems. Indeed, the new generation of communication systems is a real challenge for system designers. On the one hand, by the complexity of architecture which implies a greater number of circuits, and on the other hand, by the complexity of the signal involved for 5G. It is therefore necessary to be able to predict the performance of the system before manufacture. That is to say, to know the radiation pattern of the antenna, controlled thanks to the digital part, and according to the possible impairments of the circuits of the RF front-end. System-level commercial simulators allow the design of large systems and the management of signals in the time domain. Unfortunately, the proposed models don't make it possible to have sufficient description of the complex phenomenon in power amplifiers. Indeed, the nonlinearities, mismatch, and memory effects of the circuit will impact the overall performance of the system. In the rest of this presentation, we will show you the contribution of advanced behavior models for the design of complex systems. Today, original equipment manufacturers have a real need for modeling when designing their system. The main sources of information for system designers are datasheets, measurement data, or circuit design. But this comes with drawbacks, such as the lack of information that can be found in datasheets, important resources that must be brought to carry out the measurement on the components, and the complexity of the integration of the circuit design in system-level simulation, for example. Behavior models appear to be good candidates for system design that allows for a wide range of validity and fast simulation while protecting the circuit manufacturer's IP. The procedure we propose is as follows. From data coming from simulation or from measurements, we can build a library of behavior models that take into account the phenomenon of nonlinearity, mismatch, and memory. These models can be cascaded to design the architecture of a RF front-end system and can simulate it in transient envelope to predict performance. Then, this architecture can be used in a third-party commercial software, allowing a time domain simulation and be integrated with other components of the system-level simulators, such as the digital part or the EM part. Here we will take the example of a simulation of the interaction between the RF front-end and the antenna array. Here is a schematic of a simple architecture of a phased array antenna. The front-end consists of phase shifters and power amplifiers that allows to apply a defined signal magnitude and phase to each antenna elements. By controlling the phase shifters, the system makes it possible to steer the beam in a specific direction. Currently, the antenna is designed from ideal signal magnitude and phase at the input ports of the antenna. After manufacturing, a set of measurements in an anechoic chamber allows to calibrate the antenna, that is to say, to apply a new control on phase shifters that takes into account the impairments of the system and so correct the beam direction of the antenna. The measurement campaign can be very time consuming and expensive, and sometimes calibration is not possible if we didn't anticipate some effects. Indeed, power amplifiers can be affected by the mutual coupling between each antenna element. In fact, this phenomenon on the antenna panel causes a load pull effect on each amplifier. This changes the characteristics of the circuits and then the signal magnitude and phase as the input of each element of the antenna. And so it changes the beamforming. Modeling these effects is critical for high-frequency designs, especially at millimeter waves. This is also critical to accurately characterize and create models for circuits. And let's see how to do this. So first, how to extract behavior model. The extraction of the behavior model can be performed from load pull measurement. It consists of obtaining the EM and EM characteristics for several output impedances and several frequencies in the band of the application signal. The operation can also be done from a circuit simulation if the design is available. These load pull data are used to extract a behavior model that can reproduce the nonlinearity, mismatch, and the short-time memory of the circuit. Here we present the gain curves as a function of input power, frequency, and output impedance. We see excellent results from the behavior model. Also, with this modeling tool, you can extract a behavior model of your antenna designed into an EM simulator. After an EM simulation, our modeling tool imports S-parameter file of your antenna to be able to take into account the mismatch with the power amplifier and the mutual coupling between each patch. And also the far field data provided by the EM simulator are used to be able to plot the radiation pattern. Now, thanks to the power amplifier model and antenna model, we can start to design our system into a system modeler. So Vision System Modeler is a simulation environment that includes a schematic editor in which we can connect our PA model to the antenna model. In this example, we address a 4x4 phased array antenna. So we must connect 16 PAs to the 16 ports of the antenna model. This kind of operation can be quickly laborious, especially if you address systems with hundreds or thousands of elements. To facilitate the design of this type of architecture, a new mechanism for describing blocks and ports has been introduced. So thanks to this simplified description, you can quickly design very large architectures and focus your work in the analysis of the simulation results. About the simulation, Vision System Modeler includes a unique and robust solver that computes incident and reflected powers at each node of your design. So this simulation can predict the magnitude and phase of the incident power at each port of the antenna. The simulation is fast, so you can consider performing a large number of sweeps in frequency and power, but also apply a phase shift between the different ports and simulate the beamforming possibilities that the architectures can achieve. For example, for a 4x4 antenna, we can perform both horizontal and vertical beamforming using the variables phase shift X and phase shift Y defined by the user. If we sweep each of these variables from 0 to 360 with a step of 1 degree, there are over 130,000 cases to be simulated. Vision simulation tools give you the result in 30 minutes in CW mode for a full scan of the antenna beam. Here is the results of a simulation in which we swept the value of phase shift. In this graph, we show the variation of output power of 4 PAs according to the horizontal phase shift. We can clearly see the impact of the load pull effect on PAs. Vision integrates an export feature that sets automatically in HFSS project the magnitude and phase of antenna sources. In that way, you can display radiation pattern and use all the post-processing capabilities of ANSYS HFSS. Finally, we also offer the capability to plot the radiation pattern in Vision, so you can check directly after the simulation if your beamforming is correct or not. Here are some examples of radiation pattern displayed in Vision in which we can observe the beam distortion according to the phase shift. Here we will present another example of the use of behavior models that involves the interaction between the front end and the signals generated by the digital signal processing part of the system. The interest here is to be able to produce a simulation bench for the design of an amplifier linearization system. Before to present in details the behavior model, a few words about the origin of memory effects. We separate two types of memory according to the time constants involved, long-term and short-term memory effects. The short-term memory will concern the transit time in the transistor and the group delay related to input and output matching networks of the amplifier. it will have a major impact on the carrier frequency of the signal, and that's why we call it high-frequency memory. The long-term memory concerns the thermal and trapping effects, but also the modulation of the BIOS circuit. The envelope of the input signal having a slow variation, and so a low frequency will therefore be sensitive to this long-term constants. To illustrate this graph in the center shows the dynamic gain of a PA for a modulated signal. We can clearly see the impact of the PA's memory, which cannot be represented by a simple static characteristic. It is therefore necessary to model the PA with a more complex characteristic in order to be able to predict the response of the PA to a modulated signal. The amplifier model that we use is called the two-path memory model and allows these two memory effects to be represented separately, the high-frequency and low-frequency memory. This model is also available in our modeling software platform called Vision. That's why we're going to name this model Vision model. In this diagram, we represent a first path was the short-term kernel is characterized by a CW signal, whose power is and carrier frequency are stripped. This corresponds to recovering the EM/AM and AM/PM characteristics. The second path represents the long-term memory through two kernels characterized by a carrier frequency at the center of the operating band, and this carrier is modulated by a lower power tone. The characterization consists of varying the power of the central frequency and the frequency spacing between the two tones. This type of characterization can be done in circuit simulators. To apply the Vision model, we use a reference design available in ADS, on which we perform a two-tone test. This graph shows the EMD3 response of the circuit for several input power levels, and for different spacing between the two tones. In red, we find the left EMD3, and in blue, the right EMD3. This graph clearly shows the asymmetry in left and right EMD3, which is a manifestation of a low frequency memory. And this type of characteristic is impossible to reproduce with a model without memory. We use the Vision model presented previously that we implemented in a dataflow type system simulator. By reproducing the two-tone test, it can be seen that the Vision model is able to reproduce the low-frequency resonance of the circuit. As this graph shows, the static models, the EPHD model available for system simulation, are unable to reproduce the low-frequency memory. The model that takes into account only the high-frequency memory seems to take the asymmetry but not the resonance. And again, the high and low-frequency memory model performed very well on the two-tone test. In this example, we integrate the Vision model into System View and compare the output spectrum of the circuit obtained from a circuit envelope simulation in ADS, and also the Vision model and the static PhD model. The signal used as a 64 QAM modulation with a 5 MHz bandwidth. We can observe that the static PhD model in blue predicts a perfect symmetry between the left and right ACPR, which is not compatible with low-frequency memory effects we have seen. Also, we note that the simulated spectral regrowth on the right side is overestimated by around 5 dBc compared to the circuit simulation used here as a reference. Finally, we can see that the simulation performed using the Vision model predicts the asymmetry between ACPR right and ACPR left as expected. It shows a clear added value over the static PhD model, which does not exhibit this critical characteristic that is needed to be taken into account if the amplifier was to be linearized. Vision model is not only accurate for basic stimulus like two-tone signals, but it's also well suited for wideband modulated signals. On the contrary, PhD models show clear limitation when used for other than CW input signals. In this other example, we compare simulation performed in Simulink MATLAB, where we have also integrated the vision model. We compare the model with the static model available in the Simulink library. We change the signal band from 5 to 20 MHz, and we see that the spectrum of the vision model reacts differently by taking into account the low frequency memory, while Simulink static model exhibits symmetry between the left and right ACPR. We decided to evaluate a linearization algorithm on these two models from the modulated 5 MHz signal. The tools available in Simulink are used to estimate the DPD coefficients and apply them in the DPD block. The DPD model chosen here is the GMP model, the generalized memory polynomial, with an order of 5 for the nonlinearity and 5 for the memory. We see that the DPD algorithm is working on the two models, and also we see that it is more efficient in the case of the Simulink model without memory. Now we increase the signal bandwidth to 20 MHz while keeping the same orders of the DPD model. We see that the algorithm is still working on the model without memory, while it explodes on the case of the vision model. So the benefit of using the vision model, representing as closely as possible the behavior of the circuit, ensures that the chosen linearization techniques will work in all use cases. That is to say, different signal bandwidths, peak to average ratio, or average power. And this before implementing the algorithm in the FPGA. So to conclude, we have seen two examples of behavior models applications, allowing system designers to understand the interaction between the front end and the antenna on the one hand, and the design of a linearization system on the other hand. The model of the first example is focused on the capability to predict the performance of the PA under load pull effect that allow to predict the correct radiation pattern. And the model of the second allows to take into account the high and low frequency effects to evaluate in simulation a DPD algorithm before implementation in FPGA. So these two new advanced models are available at system level simulator to address the design of the new communication system. Thank you for your attention.